All right. So if you remember at the end of the last class, before we get to the whole debate part, we ended up at 3 basic rotation matrices, right? Along x-axis, y-axis, and z-axis. You can use them. If you can memorize, you can put them in your cheat sheet. You could also find them the way that we did with the z-axis and y-axis. So you don't have to absolutely memorize them, but it's a good way of knowing how to drive that. Now, we are going to use those 3 as our base rotations every time we come across rotating a reference, or there are 3 different common use of rotation matrices, at least in our application. You can represent an orientation. So here is orientation, right? If I go, like, if this is my fixed frame that is on the corner of the wall, right? If you remember, so our reference for our fixed frame is going to be in that corner. So if this is a reference frame that's on me, and I want to know my representation with respect to the class, that's one way. My reference frame compared to that one, we find the rotation matrix 3 by 3 in 3D space. The other, if we need to change our reference frame, let's say that there's a car, we have a robotic car, like a mobile robot, there's an arm on top of it, right? The car is moving, so there is a fixed frame on the car. And then this robot body has, let's say there is a point that we want to assign the glitter of the arm, to point B, let's say. You know what is the location of point B in this reference frame, right? So if you wanted to know the point, location, and orientation, if you wanted to do an vector with respect to a different frame, you can use the same rotation matrix between these 2 frames. So same rotation matrix where this object is, where a point of this object in this frame is with respect to that. You could also rotate a vector or frame and use rotation matrix and be able to transfer between frames. All right. So every time in robotics we talk about things, we assign a reference frame to them, then we talk about that. So where am I becomes very important every time you are discussing anything. You're going to cover all 3 applications today, hopefully, if you have time. Should be able to. All right. The first one is pretty straightforward based on what we have learned so far. So we always will assume a fixed frame, right? Here, you see that this is my fixed frame. And we said in our classroom is going to be the corner of the room. Here, the paper is going to be that Z to the top, and then we have X and Y. So we just need to know the direction of Z. The other 2, we can figure it out. So that's going to be our fixed frame. And if you see that in your textbook, they drop the notation, they just show Z axes. It is because you know, if you know the direction of Z, where is the other? So whatever literature you're reading, check how they use, what are the notation they're using. It might not be the same as what I'm using, or 2 books might be different, but the concept is the same thing. All right. Now, let's see that that's our fixed frame S. Now we have a frame called A. We are going to represent that to see what's the direction of this frame with respect to our fixed frame. You should be able to write the rotation matrix using the direction cosine or using the projection method, right? So if you look at here, RA, you see that I didn't say with respect to Y. What? This is RSA because I'm representing it in the S frame. So I kind of dropped that first one because I know that's my fixed frame. So frame A with respect to fixed frame, the x-axis is in the direction of x-axis 1, and then there's no component in Z or Y, so 0, 0. Y-axis is in the same direction, so 0, 1, 0, so it doesn't have any element in other. Z-axis is also, well, this is Z-axis, well, is in the Z direction, 0, 0. So you see that my frame A doesn't have any rotation with respect to my fixed frame. but there is a rotation matrix for it. What's the rotation matrix? Identity, right? Meaning that all the axes are in the same direction. So if we needed to do matrix multiplication, we have something multiplied by 1. So nothing will change going through this one frame. Now, if you look at frame B, R of B with respect to your S frame, I'll let you in this time. With respect to this, our fixed frame, you see that the x axis, sorry, I have this here. The x axis has element in y direction and then nothing in the other two. So 0 and 0, because these are rotated 90 degrees, so we know it's just in one of the axis direction. And if you look at the y of b is here, right? Y of b. So it's -1 in xs direction and no element in the other two. So you should be able to write these three by looking at the new frame. So frame A, B, and C. So this is a good practice when you're studying. Grab one of these and see if you get to the same rotation matrix. Now, we represented frame A, frame B, and frame C with respect to a fixed frame. What's the representation? A rotation matrix. Has 9 elements, 3 by 3. Does that make sense? Yes? Okay. Now, sometimes we have a fixed axis, right? So we wrote all the, let's say we have a camera, we have a robot arm, and we have someone that is watching, right? So bystander has a frame on his own. Now, let's say that I want to know what's the rotation, what's the transfer, what's the mapping between frame A and frame C. Now, if you remember this, the first subscription is the old frame or the original frame. You're trying to find rotation with respect to them. So C, so I want to know how can I represent C in frame A? Right? So that's how you will read it. Now, to do that, you will check. You should be, it should be able to arrive to that matrix. I'm gonna draw with a different color, blue. So I want to know where x of c is. So here is x of c, right? You see that it's in the direction of z and no component in the other two. All right. So, and the rest. I assume that you can do that for yourself. Now, do you remember one of the specification of SO subset? We said that the transpose is equal to the inverse. Now, what if I wanted RCA? Is the inverse of the other one? Well, we're just going to transpose AC because that was one of the specification, right? So if you have a matrix, if you have a rotation one way, you have the other way. You just have to do like one step, like math operation on it, right? So for rotation matrix, for 3 by 3s, we can do this. We can say RCA is going to be RAC transpose, which is RAC inverse. Now, finding transpose is easy, right? We just put these rows and columns over, so you don't have to find the inverse, because for inverse is, I know you have to go to like extra steps, what is meaning, and then all those. You don't have to do that. All right. But if I ask an example or homework, you need to write this. By knowing this, I'm just going to write it. So that was representing a frame, a reference frame, or represent a relation between two frames with respect to a fixed frame. All right. The other use is changing the reference frame that I talked about. Think about that mobile car. You have a point on it, and then you want to express that point in different reference frame. So you're changing the reference frame of or your point of view when you're talking about that point. Now, we have those 3 frames. I think they are the same ones. Sorry. One way if we want to find RBC, so we have, let's say we have RA, so these are all SA, RSB, RSC. Let's say we have this, we just saw how to do that. If we don't have RBC directly, like I want to know how to say, we see that point P. I want to know what would be the position of point P, for example, in different reference frames. If I know it in one of the reference frames, and I know the rotation between all the frames, I can tell you what's the position of P in any of those. Now, one trick is to find RBC. If you have RSB, you have RBC, you can find it, then you can use the subscription elimination to find the third rotation. So if you want RSC, you can say RSB, cancel, cancel, is going to give you RSC. So if you have two of them, you can cancel the subscription to get you the third. So how do you cancel? You multiply them together. So basically, instead of doing a visual, writing a rotation matrix from visual, if you already calculate them, you just have to multiply them. So let's say I gave you RBC, and then I gave you RSP, and I asked you what is, for example, RSC. If you can find this relationship between subscription, all you have to do is multiply those two, for example. You cannot, when you are doing the subscription cancellation, these two have to be next to each other. Here, let's see. We want to find RAC. All right. So RAC, meaning that reference frame C with respect to A, right, is going to be, let's say I know what is the rotation between these two. I also know the rotation between these two. I want to know what's the green one. All you have to do, then RBC, multiply them, and it will give you that rotation. Because they commute, there is a relation, you can go. Now, let's say you didn't have RBC, but instead, so let's say you didn't have RBC, but you had RCB. What would you do? Transpose. So you will write the transpose here, because you know the transpose is equal to the inverse. So that plug it in here, and then you have it. So you will have the rotation one way, and you can get the transpose to get the rotation the other way, and fine. Now, this relationship, if any of these are missing and you have the other two, you can find it. Let's say you're looking for RAC. Let's say no, you're looking for RAB. You have RAC. So this is another example here. Let's say you have RAC, and then you have RAB. Let's go with that. How do I find RBC? It's a matrix comes down to matrix multiplication, right? So if you had to find the inverse of whatever is left, you get the transpose of that, because the inverse is equal to transpose. So you see that we are getting close to using math and basically matrix multiplication in our robotic application, moving the reference frame. Don't worry about it, we'll solve enough problems that you'll get to know different way of doing this, but the fundamentals are as simple as this. You find the relationship, the mathematical relationship between your frames, and then you perform the operation. And the beauty is that you can actually look at your frame and see, yes, that's how they are doing. Now, let's say that I have a point P in frame B. I know the location, I know how it is configured, the position. let's say P is on the negative 1x and 0 and 0, with along this axis on the negative side, right? I want to know what is this location from the point of view of my fixed frame. So let's say this is my mobile robot. There's a point B that I know with respect to the mobile robot is going to be negative 1, 0, 0. I want to know what's that point with respect to the corner of the room. To do that, you ignore my face there. That, I think I do that, yes. To find that, we're gonna say that, well, we have PB in the frame B. If we have the rotation matrix, the mapping between this frame and this frame, you can use that and perform the matrix multiplication to find the position of this, because that was my promise, right? If you know the relation between two reference frames, anything between them, you can find where everything is. Where a point is, where a vector is, how you rotate the vector. All you have to do is PS, location of P with respect to this frame. So I'm not actually moving it. So let's say, let's use that. This is in the negative direction of where, right? X. And I want to know what's the position is 1, 2, 0 in this frame, which is my hand, my body. I want to look at you are in from the corner of that room. What's the position? And I have the relation between these two frames. All you have to do is pre-multiply the rotation matrix by the position. And you see that the subscription rule applies. It's kind of a cheat, but be careful, don't go by that. This is always pre-multiplication. So 3 by 3 times 3 by 1. What's the solution? 3 by 1. So you're checking, making sure that everything makes sense. That would be the position of your point with respect to another frame. So let's say, well, we have the position. So PS is going to be 0, 1, 0, whatever that. So you can find that relationship, right? I'm assuming that you can do that. RSV times negative 0, negative 1, 0, 0. Do you remember I said you should be able to perform matrix multiplication by hand, not calculated? That's what I'm talking about. So row by column, row by column. I don't want you to use calculator for that. But if I ask you to do 3 by 3 multiplication, I probably will let you use calculator, which is your homework one, as it just takes a lot of time and you can make mistakes there. Does that make sense? What we're trying to do and how we're using math in our benefit, right? Third way is rotating a vector. Why do we care about vectors? Let's say you're talking about speed, you have a direction, right? You're talking about force, you have a direction. So that's where vectors come in. So what if we wanted to, let's say, rotate a vector and then see what would be, so we have the velocity of this vector in this direction, and then we're rotating it direction by some angle. And we are seeing that frame. Can we use our rotation matrices to find the new direction of this vector? Yes, we can. Now let's see that, let's say our original frame is frame 0, and our vector, the speed, the direction of the mobile robot that's moving is in V0 direction. Now let's say that this V0 even has a value. First of all, whenever you are talking about position velocity, these are all column because they're usually post multiply, but you can usually write them or see they are written this way. This just means, so Vx, Vy, Vz. That's all it means. So especially when you're coding, you want to write them and then put transfer. So less space taken. And it's 0 in X direction, 1 and 1 in Z direction. So this is actually, the value is not unit vector because it won't be unit vectors. It's actually a velocity, that the velocity vector. Now, if this vector is rotated 90-degree along y-axis, and we want to find the new direction of this V, based on what you just learned, what do you think you should do if I want to find V1? I rotated, and we said that you pre-multiply a vector. So your previous vector was a position, right? Now your new vector is a velocity. So we want to know if you rotate this, if our frame rotated. So let's say the car was moving and I'm driving and I go fast on the corner and I put the car. I have done that before. Feedback. Oh, I might have to slightly quiet the water that was not the. So the reference frame is still in the car, right? I was going straight and then I didn't probably see the corner and I came back. So you want to know at that point, I was going, let's say however many speed. The frame rotated, so the reference frame rotated. I was going the same direction, which is why it happened almost flip, right? So if I want to freeze the time and see what was the direction of the vector, all I have to do is what was this rotation matrix and multiply it by the original velocity direction. It will give you the direction. Then the car was going this way, flip over, this is the velocity. You don't need to calculate the whole thing. The beauty is when you are analyzing the system and you say go in this direction and turn, if you have the reference frame and you have the information of the motion, you just write the code and increase the time. Tell me at 10 seconds what the direction of the car and the position, the code, the analysis should tell you because it's moving the reference frame along the way. If anything, if there's any rotation, you should be able to tell all the properties and configurations. You have the rotation information. Does that make sense? That's why it is useful to use rotation matrices to know how a vector would rotate. Because usually you won't rotate a vector, but things happen, like on the corner or accident, and you want to know what was the direction of that velocity. If you know how the car rotated, you can tell me like what's the projection of the car would have gone. Right? So the reason I'm bringing a lot of so this is a kind of pause, a lot of life experience and tell you about them. Well, first I want to call the class to be fun and connect on personal level. Second, how closely you're actually dealing with these phenomena and fundamentals that you're learning in theory. So to me, sometimes something happens. This was the second law of Newton or something. You know, if you're a little bit nerd, it happens a lot. And it's like, oh my God, like my bike is actually like I use a mountain bike. This is precisely where I'm talking. So there are two group of people. One, you just hear the theory, check a box, get a grade. There's the other that actually use the knowledge and try to connect. So your instructor, your professor does it a little bit for you, but it's up to you to connect those. So I'm kind of showing you some of the examples, like where I see them in real life application. All right, I want you to do that. So take this as a little bit of joke, and also there's something behind. I did almost crash on a turn because of the poisoned water, but so my dog was in the car and she got hit to the window, like front show, because she was not, you know, taxing. But if I had a reference frame on her and I could tell exactly model how she moved, right? Yeah. So I'm hoping that you can pick this up and then maybe do it for yourself, like when you are dealing with these scenarios. So we're gonna do the attendance. I'm gonna change the date to today. There's gonna be a password. Of course, because it's me. Because I know you saw the password, right? Seriously. Yeah, I'm gonna resume this. All right, good to know. You should know your audience. But all right, back to our very fun topic. So now our new V, I'm just gonna shorthandly call it V1, is going to be whatever is the rotation matrix here. So I can actually do this full screen. So the rotation matrix, you should be able to find it now by observation visually. So you kind of leveled up your level 2, so you can use your visualization. So Adam will be fine. And then do the multiplication, let's say it's 110. Okay, that's so what rotation matrix here did, it acted as an operator, right? It rotated one vector 90 degrees. So pretty neat. The last one, which is probably the most important, and we will use this a lot, is rotating a frame about an axis or vector. We have done rotating about an axis, right? X, Y, Z, or multiple rotation about that, or rotating about a frame. So you remember I said those are your principal or basic rotations. The reason is that, let's say this is a vector that has some component in X, Y, Z. Any vector you can find your X, Y, Z in the representation, right? What if I rotated about this? Remember the screw motion? So in reality, the rotation actually happens about an axis that could have two components in the three axes or all three components. So those are our general rotations. Now, your basic or principal are a subset of your general rotation, right? So we usually start with the simple one, but then that means life is more complicated. So life is more like this, rotation. Now, what is C theta? That's shorthand for cosine of theta. So cosine of theta, we write C theta. This is very useful when you're coding, so you don't have to write every single time. So you can say what, like, kind of introduce a variable for them. So here, if you have a vector omega, and this vector has three components in X, Y, Z direction, the rotation matrix, if this was the axis of rotation, would look like that. So general rotation. Now, if you make this 0, 0, become rotation about X, go ahead and look here, you will get that basic rotation. Right? So in your cheat sheet, you want to put this one, you want to put those three. And you'll actually use this rotation about an axis in one of your PA assignments. But I won't tell you which one. You have to be able to find it out. It's not next week, that I can tell you. All right. So we talked about all three common use of rotation matrices, correct? Now, let's say that we are rotating. Let's start simple. We are rotating about our principal axis, the three basic rotation. Now, we have multiple rotation, consecutive rotation. There are two scenarios. Should not get them confused because they will give you two different rotation matrices. And the real life effect of making a mistake is, instead of let's say that there was a portal and you're trying to send something through that portal from the rotation. If you wanted something to land by that door, if you write the rotation matrix wrong, it's gonna land over here. All right, so they are very important if you know what you're doing. The first one that I think the easier one is rotation with respect to the current, meaning that this is a frame on top of this object, right? I assign the frame here, and this is z direction, x and y. I'm gonna say rotate theta degree about z axis. Now rotate theta 1 degree about x axis. You see that? Now rotate another theta about the y axis. Rotates about its own. So it's carrying its own reference frame. This is when you have rotation about the current frame. You're carrying the frame with you. In this case, we will post multiply the new rotation. So let's say the z frame 0, x0, y0, z0 is our original frame, and I'm rotating p angle. So this one is p. So my first rotation about frame 0, I'm going to write here so you know about frame 0. The first rotation about angle axis y and for theta. Then my second rotation is about the current z frame z1. So I'm rotating about z1 and for theta. So about z1 for theta. So this is frame 1, and I keep post multiplying them, right? At the end, when you multiply all of them, it gives you your final rotation. This was rotation on y. This was rotation on z. This is one scenario, yes.
So when you're generating a comma between any sort of angle, that's mean we're multiplying by the completion.
Yes, rotation is about an angle.
Okay.
Yeah, you're rotating about an axis, around an axis, right? For an angle. So the variable, you can call it theta, phi, psi, whatever. Variable is whatever you choose. You can call it theta 1, theta 2. So that's rotating about the current frame. Now, or sometimes I might say body frame. It's the frame that is on the body and is moving with it. The other one is rotation with respect to fixed frame. Do you remember the fixed frame there? So this is my object. And assume at the beginning, x, y, z of both are in the same direction. So this is z of that and x and y. And I say rotate t about z axis. Let's start with z there and with y. So let's start with y, the first one. About y 0. So x and y. So the y of this and y of that at the beginning are the same. So let's rotate about y. Then I say rotate about z for theta. So the body frame z changed, but I'm rotating about this frame. The z of this frame is still this one. Right? So they will end up in different configurations. Now, how do we calculate that mathematically? Because whatever you see, you should be able to write the equation for it mathematically. If you pre-multiply the rotation, you will get the correct answer. Now you see that you cannot switch the rotation order, because if you did, you will end up somewhere else, right? Now, you will see that here, for example, this Z2 might not be exactly this Z2, because in the first scenario, Z1 and Z2 are the same. In the second scenario, it's showing that Z2 will have a different direction. So this is a general view of that, meaning that pre-multiplication and post-multiplication will impact the configuration of your reference frame, where they're pointed out to. For a better example, let's look at this. We are going to perform a pre-multiplication and then a post-multiplication and compare them. Let's say this was our fixed frame. This is our body for current frame. All right. My first rotation is going to be, so this is my current frame. or body. So I'm going to find the rotation of my frame if I rotated 90 degrees along my fixed frame, about the z-axis. So z-axis of your fixed frame. If you rotate that, your body frame will end up here. We call this RSB prime to just show that the new frame is called B prime. And we rotated about the fixed frame 90 degrees, the z-axis of the fixed frame. Now, if I say, you know what, I want to rotate about the z-axis of my body frame, the current frame. Is positive direction is this, positive direction is this way. Now, if you rotate that way, so your y goes down, your x of b will be here. So you see that your RSB second, how do you say that? Double prime? Double prime, all right. You see that this is a totally different configuration, right? All you did was rotating about z-axis from different perspectives. Now, the mathematics will give you these correctly. But if you're trying to do visually, sometimes you have to just make sure where you're rotating to, or with respect to what you're rotating. So post multiplication and pre-multiplication are important. Pre is for fixed frame, post is for your current frame. So as you go, you multiply and you rotate your frame, and you rotate around the new axis, right? For fixed frame, you always rotate about the same axis that you originally did. Now, class participation, we have enough time, thank God for this one. I think, so you only have to do class participation today, you already did the other one. So, I want you to find the rotation matrix after the following consecutive rotation. Now, there are 5 rotations, all right? Let's say you start from a fixed frame, we can say VXY, right? And then imagine you have a mobile robot. That doesn't matter. Now, what I would want you to write R equal to R different R's, how they are known. The first rotation is theta about the current axis. So I'm going to do the first one so you see how do I write it. So the first one is R about X for theta angle, right? And I'm going to write down here my final R is going to look like, and I'm going to put this R, X, and theta in the middle because I don't know if I'm going to pre-multiply or post-multiply. Then write all the other notations here and decide where you calculate. Once you have it, submit this to us. Yes.
So we're saying that after the first one, you're seeing the second one, third one.
So those are 5 consecutive rotations, but the first one happens about current axis, the second one, the current axis, then you're rotating on the fixed axis, the current axis, and the fixed axis.
So I'm confused, like post multiplication that deals with 2 rotations, right?
No,
Like,
multiply. I just brought an example for 2. So let's say here is current. I'm going to show 3 rotations, right? This is V, right? V, X, Y. First rotation about the current axis V. Second rotation about the current axis Y. Rotation about the current axis X. Rotation about the current axis. This is very different if you had them rotated about the fixed or you had a combination of them. The math is different. And if you have more than 2 rotations, you won't be able to tell me visually where your axes are going to land. You have to do the math. That is the one. I help you with the notation. So this is the first rotation. This is your second rotation. I'm gonna write Z axis 4 feet. This one is R, Z, and alpha. This one I can write R, Y, and beta. This is basically making sure that you know how to do the notation. R, X, and delta. Now, post and pre-multiply depends on if it is about a fixed axis or a current axis. The first one is this one. Then the rest of them depends on multiply or post multiply. How do you know? Go back to the last two pages and you'll know. So I'm going to pause the recording because that's going to be the end of the lecture.